Okay, so today is the last lecture, and this lecture is the last lecture in our lecture series with Victor. So the goal of my lecture today is to follow up on what he did last time and to explain to you concretely how we're going to be computing the Stark-Heegner points attached to diagonal cycles. So computing Stark-Heegner points attached to the diagonal cycles. So I remind you now a bit of the setup that we had. So we have a variety V, which is a threefold, which is going to be a product x cross x cross x of some fixed curve x. And sometimes for notational convenience and to keep track of various things, I'm going to write this product as x1 cross x2 cross x3, as Victor was doing in his lecture. But you should always keep in mind that these x1, x2, and x3 are the same curve. And then, as Victor explained, we have a correspondence from x1 cross x2 cross x3 to the curve x, which is given by a very precise cycle, a codimension 2 cycle in the product of these two varieties, and that was simply what I'm going to call x12 cross x34 in x1 cross x2 cross x3 cross x4. So when I write something like x12, I mean simply the diagonal in x1 cross x2, and x34 is a diagonal in x3 cross x4. Okay? So we have this, and this two-dimensional cycle in this four-dimensional variety gives rise to a correspondence, which allows us to transform codimension 2 cycles, or elements of the Chow group of codimension 2 cycles in x cubed, say null homologous ones, into points in the Jacobian of x. So we get this map, which Victor described also in his lecture, which I'll call capital Phi, like he did. And sometimes we'll also be interested in composing that with, we might have an elliptic curve, for example, and when we do computations, we're going to be focusing on the quotients in the Jacobian of x, which we can actually write something down. So I'm going to call this map maybe phi sub e, and then this map here, this kind of generalization of the modular parameterization, I'm going to call phi sub e, like that. Okay, so our goal is to design concrete strategies for actually calculating, given some codimension 2 null homologous algebraic cycle in the threefold, how do you actually compute the corresponding point? Okay, so given a cycle T in the Chow group, say of x1 cross x2, cross x3, null homologous, the goal is to compute the point, compute the image. Oh, actually, sorry. Let's scratch that, sorry. So what I want to mention now is sort of recalling again something that was done in the lecture of Victor. So Victor explained how given an element T in the Picard group of x1 cross x2, one can produce a null homologous algebraic cycle, which I'll call delta T, in the Chow group of codimension 2 cycles on x cubed, null homologous. So by taking some kind of fiber product of the graph of T and x3 via some projection. So there was a simple construction that allowed us to obtain this null homologous cycle. And our problem now, or the question I want to discuss today, is how to compute the image under our map phi of this null homologous cycle delta T. And the key remark which Victor made, and which I want to again remind you of, emphasize, is the fact that you don't want to use the algebraic definition in terms of intersection. So we have that phi of delta T can be written as pi 4 of pi 1, 2, 3 inverse of delta T intersected with this this two-dimensional variety x12 cross x34. So in other words, you can take this delta t, where here I have x1 cross x4 mapping first to x1 cross x2 cross x3 by a map which I'll call pi 1, 2, 3. And then we have the map pi 4, which maps to x, which is x4. So you could take the cycle here, look at its inverse image in this fourfold, intersect with this cycle here, and then push it down via pi 4, and then you would get a degree 0 divisor on x4. And that's sort of an algebraic definition of the map. But this is not, as far as we can tell, is not so useful. Oh, hold on. Okay. Okay, here we are. So this is not useful for calculation, for numerical calculation. It's very good for theoretical purposes. For example, it makes it completely transparent that when we start with an algebraic cycle defined over some field f, we will get a point on the Jacobian defined over the same field. But for calculating, we want to resort to analytic techniques. Okay. So let me now also remind you of a diagram which was there in Victor's lecture, and which kind of underlies what we're going to do. So we have this analytic formula, analytic approach to calculating these cycles. We have the Chow group of codimension 2 cycles on x cubed, naught, and we want to compute this map phi to the Jacobian of the curve x, and maybe even compose that with some modular parameterization from Jacobian of x or some elliptic curve in concrete situations. Now here, so this side is purely algebraic, as Victor mentioned, and then we have the Abel-Jacobi maps, which identify certain pieces of this Chow group and the Jacobian with certain concrete objects related to differential forms. So here the Abel-Jacobi maps this to a certain piece of the dual, the Durham cohomology of x cubed. So it's the dual of the second stage in the Hodge filtration of the H3 Durham of x cubed, modulo the natural image of the H3 of x cubed of C with values in Z. Here we have the standard traditional Abel-Jacobi map, which most of you are probably a lot more familiar with, mapping this to the dual of the omega 1 of x, which is the Phil 1 of H1 Durham also, modulo the image of H1 of x of CZ. And here we have the standard, where we have the projection to E of C, which we identify with C modulo the period lattice of lambda E. And this map here is just given by evaluation at a specific differential form, which I'll call omega sub E, in omega 1 of x. Okay? And the formula which Victor wrote down last time is that so we can understand phi of delta t, phi sub E rather, there's this map here, I guess, which as a map to C mod lambda E, we can write this as the Abel-Jacobi of the cycle delta t evaluated on the class of delta 1, 2, the class of the diagonal, tensored with this differential omega E. So that was the formula which we saw last time, where here I remind you that the class of the diagonal delta 1, 2 is an element of the Phil 1 H2 Durham of x1 cross x2 intersected with the H2 Durham, intersected with H2 of x1 cross x2 with values in Z. So the Betty cohomology of, so it's a cohomology class which has at least one holomorphic component, in fact exactly one holomorphic component, and has also integral periods. The Hodge conjecture tells us that any such class here should come from an algebraic cycle, and of course here it does by construction. As a very simple example of a Hodge class. And then omega sub e here is an element in fill 1 of H1 Darmon of this X, and by construction, so it's an element of omega 1 of X. And so the tensor product of these two things lives really in here, in this fill 2 H3 Darmon of X cubed. Okay, so this kind of makes sense, at least on a formal level. And we're going to use this formula then. So our problem now is to actually calculate this numerically. So for this Adel-Jacobi map here on this line, it's not so hard. I mean, the recipe here would be to take this cycle, delta t, which is null homologous, write it as the boundary of a three-dimensional region, and then integrate this differential form over that three-dimensional region. You get an invariant modulo periods, okay? The difficulty here, of course, is actually finding this three-dimensional region whose boundary is the cycle of interest. So we want to see how to do that in practice. Okay. Okay, so the first step, which Victor outlined also in his talk, is to reduce this formula that I had. What am I doing? Let me keep this here. This formula that I have here, where the shape of this formula is that we have a fixed modular parameterization phi sub e, or here we have this fixed Abel-Jacobi map, but we're evaluating on a fixed differential form, maybe this one, but on a varying collection of Hodge classes, of codimension 2 cycles, these delta t's, as t varies over certain Hodge classes. So I'm going to now give you a variant of that formula, a variant of this formula, where which involves the very nice null homologous cycle, the gross Kudla-Schoen diagonal cycle in the triple product. So I remind you that this delta gross Kudla-Schoen is essentially, the interesting part of it is it's the principal diagonal in x1 cross x2 cross x3, which I denote by delta 1, 2, 3. I guess I could have also written it as x1, 2, 3 in the notations that I had before. And then so this cycle is the one of interest, but it's not null homologous. So one has to modify it a little bit to kill its class in cohomology. And one does that by subtracting the various subdiagonals. So I take minus delta 1, 2, minus delta 1, 3, minus delta 2, 3. And then I add in delta 1 and delta 2 and delta 3. So these sub-cycles are defined by choosing a base point, which I'll call P, a fixed base point. So for example, delta 1, 2 is the collection of all points of the form x, comma, p, as x ranges over x, over the curve, and p is this fixed point. Okay, this one here is going to be the set of all things of the form x, p, and you get the general idea. Okay, so this is a cycle. It's codimension 2. It's a Chow group of x cubed, codimension 2 cycles, and one can show that it's null homologous. Okay, so now the formula which is going to be used, which we'll be using in our calculation. So you want to understand the Abel-Jacobi of this cycle delta t evaluated on this fixed differential class of delta 1, 2 tensored with omega e. Now the problem about this formula, if you just resort to the original definition for the Abel-Jacobi, you have to, the recipe tells you that you have to find a way of expressing delta t as the boundary of something three-dimensional. And if that cycle is varying, then the complexity of the calculation is pushed into the cycle. You would like a formula. Well, so this formula here that I'm going to write down allows us to transfer the complexity to the calculation of the specific differential form. So we can write this as Abel-Jacobi of the gross Kudla-Schoen cycle evaluated on the class of T tensored with omega E. So this right-hand side is a little bit easier to compute because now we're dealing with a fixed cycle in the threefold. And what's varying is this class of T, this particular Hodge class associated to a divisor in x1 cross x2. In practice, in our calculations, for those of you who are in our group for the project, you're going to be handed a specific Hodge cycle, and then your task is going to be to compute this. Okay. So we're going to be using this formula because what we're really going to be interested in is the right-hand side. That's what we're going to be calculating. And the proof of this formula, I don't want to get into it. We can discuss this maybe in the evening sessions for those who are in our group. It's a very formal calculation. You can basically resort, if you stare at the definitions of these two sides, the algebraic definitions in terms of intersections of cycles, you will see that in fact, they're just two different ways of looking at the same object. So the identity kind of follows from a rather formal calculation, directly from the definitions. Okay. So now we have this, okay? And maybe then the third remark I want to make, having now reduced ourselves to computing this, is so the class of T is an element now in H2 Darmon of x1 cross x2, which by Knuth can be decomposed as H2 Darmon of x1 tensor H0 of x2 plus H1 Darmon of x1 tensor H1 Darmon of x2 plus H0 tensor H2. Okay, so you have these three pieces. And for us, the H2 tensor H0 and H0 tensor H2 pieces are a little bit extraneous. We don't want to deal with them. Turns out they don't give us such interesting points anyway. So Victor sort of explained or alluded to the fact that we had a way of projecting this class onto the interesting piece, which is the H1 tensor H1 part. So for our purposes, what we're going to do is we're just simply going to assume that our T is such that a cycle class lives in the H1 tensor H1. It's a very simple modification. What you do is you have your cycle T, you look at its horizontal and vertical projections, and you modify T by appropriate multiples of the horizontal and vertical projection so that these H2 tensor H0 components vanish. Okay, so what we're going to do simply is assume, without loss of generality, that we're in that situation. So assume here without loss of generality that that the class of T is in H1 Darmon of x1 tensor H1 Darmon of x2. Of course, it's still a Hodge class, so it belongs to fill one of that H1 tensor H1, and it has integral periods. That's implicit in how we obtain this class, okay? So now I want to give you a formula for Abel-Jacobi of the Gross-Kudla-Schoen diagonal cycle, modified diagonal cycle, evaluated on a general class, which is in the form omega tensor eta tensor omega e. So this omega e is not varying for us. I mean, this omega e is the differential which is attached to the elliptic curve. In practice, when we move to modular curves, we'll see this is related to a specific custom of weight 2. But this omega and eta are classes which are related to the class of T, this Hodge class. Okay, and I'll say later how we were going to write down some nice examples of those. Okay, and the key, the main ingredient in this formula are going to be the iterated cycles, the iterated integrals, sorry, which Victor mentioned in his talk, and I'll quickly recall what they are because they're fundamental for us. They're the main computational tool that we have. So what is an iterated integral? So these are objects that were introduced by Chen and later described in a more algebraic context by Haynes and many other mathematicians. So they give you a way somehow of understanding not just the first cohomology of a curve, but some part of the fundamental group of the curve. So they're invariants that are finer than just periods, and they detect information not just about the abelianization of the fundamental group, but about what's called the unipotent completion of the fundamental group. Yeah. Oh, I'm sorry. Yes, it's Hain without an S. Yes. Yeah. No E even. Okay, I'm sorry. Yeah, because there's also a mathematician called Haynes, so I'm confused. Yeah. So, in fact, I think Haynes spoke at the AWS a few years ago. No, thanks. Okay, so iterated integrals. What are they? So that we given a path. So I'm going to give myself a path gamma from 0, 1, which I think of as a function from the closed interval 0, 1 to the curve, to the complex points on the curve. And given now omega and eta for me are now going to be smooth 1 forms on x of c. And so then we define the integral over gamma of omega dot eta. This dot is important. I mean, I don't mean integrated 2 form on a one-dimensional region. This is just a notation, as Victor also mentioned. So by definition, this is the integral over t2 less than t1 less than 1. So I look at this kind of triangular region where I let t1 go between 0 and 1, and then t2 goes between 0 and t1 of the pullback of omega, viewed as a function of the variable t1, times the pullback of the differential eta, viewed as a function of the variable t2. Okay. Another way of writing this, we can also write this as a line integral over gamma of omega times f eta, where f eta is the primitive of eta. Now, of course, you can't define a primitive of eta on x because eta is not exact. I mean, it has an invariant in Darmon cohomology, but you can take a primitive on x tilde, which is the universal covering space. So if you take that x tilde be the universal covering space of x of c, then this f eta is perfectly well defined. You can think of the universal covering space as the set of homotopy classes of paths from a fixed base point to some other point. And if you have a path, then you can define f eta evaluated at some path sigma, say, to be simply the integral along this path sigma of eta, right? That integral makes perfect sense. It's perfectly well defined. It's homotopy invariant because eta is a closed form. I should have said maybe here, of course, these forms are assumed to be closed. They're smooth, closed, 1 forms on x of c. Okay? So that's the picture we have here. These are the iterated integrals. So in computations, you would probably resort to this definition. You would first integrate eta to get a function on the universal covering space, multiply that function by a differential form, and then iterate again that differential form along the path associated to gamma. Okay. So now I'm going to make one simplifying assumption about my omega tensor eta, which later we'll remove. So the simplifying assumption I want to make is that I'm going to assume that the Poincare pairing of omega and eta, since these are 2 smooth 1 forms, I can think of them as elements of Darmon cohomology, and I'm going to assume that they're orthogonal to each other under the Poincare pairing. Under that assumption, one can show that if I take omega wedge, how do I want to write this? Yeah, omega wedge eta, I suppose. So, okay, so here there's a omega tensor eta is a 2 form on x1 cross x2. So I can restrict this 2 form to the diagonal, to x1, 2. And the fact that this Poincaré pairing is 0 exactly corresponds to the statement that this restriction to the diagonal is exact. So this 2 form becomes exact on the diagonal. So I can write it as D of some smooth 1 form alpha. And moreover, because omega tensor eta was in fill 1, it had at least one holomorphic component, I can actually assume that alpha, the solution of this differential equation, this 1 form alpha is actually smooth of type 1, 0. So when you write it out in coordinates, it's a smooth function times dz, times the holomorphic coordinate. There are no dz bars. So we have this object. And this alpha is going to play an important role in our formula. Okay. Now maybe you might want to ask yourself, it's worthwhile to reflect on how well defined is alpha. So any solution of this equation, of course, is not unique, but any 2 solutions will differ by something which is closed and of type 1, 0. In other words, by a holomorphic 1 form on X. So there's an ambiguity in alpha, but the ambiguity is by alpha is well defined up to holomorphic 1 forms. Okay. Now I can state the theorem. Which is the key formula that we're going to be using in our group project in the AWS, which is this. Okay, Abel Jacobi of the gross Kudla-Shon diagonal cycle evaluated on omega wedge or tensor eta tensor omega e is equal to the iterated integral of omega dot eta minus, sort of corrected by, the line integral of alpha. Now where do we need to perform this integration over a specific path, which I'll call gamma sub e, where gamma sub e is the path, so it's an element actually of h1 of x of c, z, but tensored with c. Okay? So it's a C-linear combination of paths. So I extend the integration by C-linearity to such C-linear combinations. And this is defined by saying that it is the Poincaré dual to the class omega e. So that's how omega e enters into the formula. Okay? So in other words, what I want is that, so this gamma e is characterized by the following identity. If I integrate any class in Durham cohomology, any C in H1 Durham, against this gamma e, I get simply the Poincaré pairing between omega e and Xi. Okay. So this is actually one thing that's worth noting. You see, if you look at this second term here, this integral of alpha against gamma e, well, I said before that alpha was only well defined up to holomorphic differentials. In other words, up to elements in omega 1 of x. But the integral of anything, if C is in omega 1 of x, then the integral against gamma e is simply the inner product of omega e and this C. But if these are both regular differentials, then since the Poincaré pairing since the omega 1 is isotropic for the Poincaré pairing, this is 0. So this expression is really well defined. It does not depend on the choice of alpha. Another thing to observe is that really these gamma e's are, of course, only C-linear combinations of paths defined up to homotopy. And this expression here, one needs to check, does not depend on the homotopy class representative of the path that you've chosen. And that follows essentially from this differential equation. So I sort of, maybe even before proving this theorem, what you should do is really convince yourself that this quantity is well defined, doesn't depend on any of the choices that we've made in the process of defining it. Okay. So I want to so what I'll do now, I hope to give the proof of this theorem, because in a way it's important to understand the mechanism for this, because this is how the iterated integrals arise in the calculation of the Abel-Jacobi map. But maybe I'll do this at the end of the lecture if I have time. And if I don't, we'll do it in the afternoon session with the group working with us. Okay. So I mean, I should say that the main, so there's a computational flaw in this formula, as far as Victor and I can tell at least, which is the fact that, so if you want to turn this into an algorithm for calculating Abel-Jacobi, everything looks very explicit. I mean, you will be given omega, you have eta, the path can be, omega gamma can be calculated. The only difficulty is calculating this alpha, the solution of this differential equations. When you have these smooth forms, it's, at least as far as we know, we don't really know in general how to easily calculate this class alpha. So this is a problem in this context of smooth forms, that alpha is not easy to calculate in practice. Although I'd be delighted if someone tells me that I'm wrong on this and that we can actually calculate alpha. So it would be great if we could actually have an algorithm which exploits the description of Durham cohomology in terms of smooth forms, because there are various aspects where this is more easy to calculate, the smooth description of Durham cohomology. But yeah, so this bottleneck that we don't know how to compute this alpha in general is a problem, and we're going to deal with it by resorting to the description of the Durham cohomology in terms of differentials of the second kind, in terms of meromorphic differentials of the second kind. But before I go on to that, I want to make the remark that, in fact, there is one exception to this statement that we don't know how to calculate alpha. The exception is if our Hodge class is of the form, so suppose class of T was given to you, and it was of the form omega wedge eta plus eta wedge omega, or tensor A, maybe I should say. So if the class is of this form, omega tensor eta plus eta tensor omega, there's a kind of symmetric thing under the involution interchanging the two copies of x, then what we can observe is that the restriction to the diagonal is just omega wedge eta plus eta wedge omega. So I mean, so then the class of T restricted to the diagonal to x1, 2 is just this, which is 0. And we certainly know how to solve the equation d alpha equals 0. There's an obvious solution, which is just 0. So we can take alpha equals 0. And that's what Victor mentioned at the theorem at the very end, that somehow the classes of this type, the symmetric ones, are much easier to deal with. And our formula, in fact, gives, in this case, that the Abel-Jacobi of the Gross-Kudla-Schoen evaluated on the class omega tensor eta plus eta tensor omega E is equal to the integral, so it's going to be an iterated integral along gamma E of omega dot eta plus eta dot omega. And there's no correcting factor. There's no integral of alpha because alpha is 0. And now this iterated integral is an integral over a triangular region of omega times eta, or omega tensor eta. And when you interchange the factors, you integrate over the complementary triangular region. So the total integral ends up being an integral over a square, which you can break up into two line integrals. This is just the integral over gamma E of omega times the integral over gamma E of eta. So this is something that's very easy to calculate, but only for these symmetric ones. When you have the non-symmetric class, then as far as we can tell, it becomes more complicated, largely because of this difficulty that we don't know how to calculate alpha. So, because we can't get our hands on alpha, I mean, this formula here that I wrote is great for various theoretical purposes, but if you really want to compute, it is better to work with Durham cohomology. We will work with the H1 or H1 Durham of X, which is the space of meromorphic differentials of the second kind on X modulo exact exact meromorphic differentials. So I'm going to now give you a variant of this formula involving meromorphic differentials of the second kind. Okay. For this, I need to introduce a few notations. So I'm going to actually work in a slightly restricted setting, but which is enough for all the applications you have in mind for the AWS project. So I'm going to assume that, so I have my X. I'm going to assume that X is a projective curve. I mean, maybe I've been assuming that implicitly before as well. So X is a projective curve, and I'm going to give myself a Y, which is some affine curve of a very special kind, namely it's just the complement of a point in X. So I take a point which I'll call infinity, and I remove it from X. And this is what I'll call Y. And I'm going to now assume, without loss of generality, that what? Well, let's see. What did I do? Yeah, still. Yeah, okay, here. So I'm going to assume that omega, this class omega, is in omega 1 of X, and that eta is in simply in H1 direct. So this eta is equal to, is a meromorphic differential of the second kind on X. So, and what I'm going to then try to do, and I'm going to let f eta be as before, the meromorphic primitive of this differential form eta on the universal covering space X tilde. So the important property of meromorphic differentials of the second kind is that they admit meromorphic primitives on the universal covering space, which are defined by integration. The point being that if you take two homotopy classes of paths and you integrate eta along them, then that integral is well defined because the residues of eta are zero. So what you would pick up by comparing some two integrals along two different paths, maybe I'll write it here rather than gesturing. So if I have a path P1 and a path P2, which are homotopic, and I integrate eta, here's my base point P, say. If I integrate eta along these two paths, well, eta is a singular differential, so I'll pick up in general some residues. But the residues of eta are zero, so this integral is well defined. So f eta is just the integral, so f eta evaluated at a path sigma, maybe I should call them sigma 1 and sigma 2 here, is just the integral along sigma of eta, and that makes sense. So f eta is now meromorphic primitive, which we'll be using. And then I can also consider omega times f eta. This is just a meromorphic differential on this universal covering space X tilde. Okay. So now I want to define what are the principal parts. So what is a principal part of a meromorphic differential, which I'll call PP. So principal parts, PP, principal part of a differential alpha. So if alpha is a meromorphic differential on X tilde, principal part at X of alpha is simply what you get by expanding out alpha as a Laurent series around the point X and picking up the tail in the Laurent expansion. Okay, so if you write alpha at X as a sum from minus m to infinity of some uniformizing element, let's say t sub x, so j, t sub x to the j times coefficients aj, d t sub x, okay, then the principal part of alpha at x is simply the tail. So it's the sum for j going from minus m to minus 1 of the same thing, aj t sub x to the j. Maybe you want to keep the dtx to make this really an invariant expression. Okay, so those are the principal parts, and what we now want to do is look at this differential, this meromorphic differential on the universal covering space. So this lives on the universal covering space. It's not defined on X. But we'll see that the principal parts of this differential are at least well defined on X. You can think of them as functions on X. So this is a proposition. Let's see, or lemma. It's really a lemma. Key lemma, but anyway, lemma. For all x in x tilde, the principal part at x of this differential omega times f eta depends only on the image of x in x of c. So if you take 2 points on the universal covering, there we are. So if you take 2 points on the universal covering space by the same image in X, and you look at the principal part of this differential, those points, they're the same. I mean, well, by the same, of course, they live in different worlds, you could say, but they come from a common principal part on the image by pulling back. That's what we're saying. And the proof of this, maybe I'm running a little bit late, so maybe I'll leave that to you as an exercise. It's an easy exercise. The point is that if you translate omega f eta by something in the fundamental group of the curve, then omega is invariant because it comes from a differential downstairs, and f eta changes by a constant because its d, its image under d, is an invariant differential. So this changes by a constant, so the whole thing changes by a constant times omega. But omega is regular, so the principal part doesn't change. That's the idea of the proof. Okay. Yeah, you can't see the last line here, but that doesn't matter. Okay. So now I think I'm pretty okay. So then from that theorem, so in particular, it makes sense to write principal part, to talk about the principal part at x of this differential omega f eta for x in x of c. This is a meaningful concept. It makes sense to talk about that. So now, what do I want to do? I want to state the proposition, which has been one of the projects in our AWS, one of the questions in our AWS group project, to show that there exists a differential alpha in omega 1 meromorphic on the curve x with the property that, firstly, the principal, the condition is the principal part of alpha at x is the same as the principal part of omega f eta at x for all x in the curve y, in the open curve. So with the exception of infinity, we want these things to have the same principal parts. And the second condition is that the principal part of alpha at infinity, at this distinguished point which I removed, has to be equal to the principal part at infinity of our differential omega f eta, but only up to, already like this, mod dq over q. Okay, in applications, infinity is going to be a cos of a modular curve, and the natural local parameter is going to be q. So we allow simple poles in this difference. So we can't control, given this collection of principal parts, we can't get a differential on x with exactly those principal parts. There's an obstruction to that, which is the sum of the residues has to be 0. There's no reason why the sum of the residues of this omega f eta is going to be 0, because it doesn't come from an invariant differential on x. But up to that one obstruction, we can find an invariant differential, alpha, meromorphic, with exactly that collection of principal parts. So we might be off here by just a dq over q term. So this alpha is well defined up to holomorphic differentials on y with at most a logarithmic singularity, with at most a simple pole at infinity. That's the ambiguity that you have for alpha. Oh, and then of course, what is that ambiguity? If you have a differential with at most a simple pole at a single point, that simple pole can't be there by the residue formula. So alpha is again well defined up to holomorphic differentials on x. So alpha here is still well defined, which for computations is quite useful. Alpha well defined modulo omega 1 of x. Okay, so keep that in mind. And now we have the theorem, which is exactly analogous to what we had before, but now in the context of meromorphic differentials, namely the image of the Gross-Kudla-Schoen cycle evaluated under Abel-Jacobi, evaluated on the class omega tensor eta tensor omega e, is just the iterated integral of omega times f eta minus the integral of alpha along the same path, where gamma e is the same thing, or in other words, this is just iterated integral omega dot eta along gamma e minus the integral of alpha along gamma e. Here this is a dot. Okay. And that is the formula which in the group project we're going to be using in order to calculate the Stark-Heegner point. We use this iterated integral, hoping that all the terms that appear in this formula are things that can be explicitly calculated. So now the remaining, I guess I have 7 minutes or so remaining, I'm going to sketch how the algorithm goes in the setting of okay. So now page 9. So algorithm for calculating these Stark-Heegner points. And for the algorithm, of course, we're placing ourselves in this special context where the curve x is a modular curve. So let me remind you now of the setup, which Victor also mentioned a number of times. So x for me is going to be the modular curve x naught of n of level n, and maybe n could be an arbitrary integer, it could be a square free integer, or it could be a prime. For the purpose of our project, maybe it's even enough to work everything out in the simplest case where the level is prime. And y is going to be the complement of the cusp infinity. So the obvious candidate for our distinguished point is simply the cusp infinity. And we also give ourselves a modular parameterization, phi sub e, from x naught of n to some specific elliptic curve. And our goal is we want to calculate points on e using cycles on this triple product of x naught of n with itself 3 times. And then the only question is, what is class of t? So the last ingredient I need to tell you to make this sense of this calculation is what classes are we going to take? What are the Hodge classes? And there are some nice examples of Hodge classes. So in general, of course, this would just be a sum of omega I tensor eta i's, where at least one of these guys is holomorphic. But I'm going to take a specific example here, which is the following. So let G be an eigenform on x naught of n, eigenform of weight 2 on gamma naught of n. Maybe I should have said here that this phi sub e, this elliptic curve E, corresponds to an f in S2 gamma naught of n in the usual way. By pulling back the invariant differential, you get a differential here, which is an eigenform for the Heck operators. Now that eigenform I'll call f. And here I have a g, which is, and I'm going to assume that g is normalized and not equal to f. So it's a different eigenform of weight 2, but still with rational coefficients to simplify calculations a little bit. Okay, so given this g, I have an omega g in omega 1 of x, g isotypic component, which you can calculate on the computer by counting the number of points on the elliptic curve attached to g modulo p for many p. And then I also want to give myself a second meromorphic differential, which I'll call omega g, eta g, which is going to be in the g isotypic component, or rather its class is going to be in the g isotypic component for the Durham cohomology of x, but not a multiple of omega g. We'll take any differential of the second kind on whose Durham class Hecke acts via the eigenvalues attached to g, and call that eta g. And then the class we're going to consider is simply going to be omega g tensor eta g minus eta g tensor omega g. So if we so the claim is that this, so fact, that this is actually a Hodge class in H2 Durham of x1 cross x2, i.e. it belongs to what? I mean, it belongs to fill 1 of H2 Durham of x1 cross x2 intersected with H2 Betty x1 cross x2 with values in z. So it has integral periods and it's of type 1, 1. That's what we're saying here. Okay, well, it's not clear what I'm saying here, but here it is. Okay, it belongs to this group. This is the so-called Hodge classes, which the Hodge conjecture predicts in general correspond to algebraic cycles. In this special context, we know the Hodge conjecture. So rather than writing down the cycle and computing its image under the cycle class map, which we sidestep the problem, we give ourselves immediately a Hodge class. And we then want to compute the point corresponding to this Hodge class. The Hodge classes are somehow more direct from the point of view of computations. Okay. So now let me quickly finish by giving the main steps in the algorithm, what we need to do, in other words, in our group project. So for this algorithm, it's going to be divided in several steps. So the first step is to compute the Q expansion. Oh, so finally, let me just summarize what we want to do. I'm going to define PFG. So it depends now on two forms, F and G, normalized forms of weight 2. This is simply the Abel-Jacobi of the Gross-Kudla-Schoen cycle evaluated on omega g, eta g, minus eta g tensor omega g, tensored with omega sub e or omega sub f, corresponding to this form f. That's what we want to compute. And this point P sub fg is going to be in C mod lambda e, which is e of c. So we're going to get a complex point by evaluating the corresponding iterated integral, and our goal is to evaluate these complex points and recognize them as rational points on the elliptic curve ultimately and see how they behave. So how do we compute this expression in practice? So the first step in the algorithm is to compute Q expansions for omega f and omega g. This is a standard calculation. If omega f and omega g, for example, are given to you in terms of the elliptic curves, there are nice commands in various software packages which will just give you the Q expansion of f and g by essentially counting points mod p on the elliptic curve. This is something we know how to do, and we get these Q expansions, then f and g, sum of a n of f, q to the n, and likewise for g. And these are holomorphic, so they start off at n equals 1. Step 2, we need to compute the Q expansion of the meromorphic differential eta g. This is a little bit more complicated because there's no nice formula for getting eta g from, as far as I know, from the, and also eta g is not uniquely defined. It's only its class in the Ram cohomology which is well defined. So it's just some meromorphic differential. So one approach to doing that, which maybe is not the best, I mean, it's the one that Victor and I came up with before coming to the AWS, but we don't claim that it's the most efficient. So you want to find a basis for the de Rham cohomology. So of course, you can take omega 1 up to omega t to be a basis of omega 1 of x. And that is just the modular forms of weight 2 on gamma naught of n. So there are many algorithms for doing that, using modular symbols and so on and so forth. And then we're going to let u be an element, be a regular function on y with minimal order pole at infinity, with the order at infinity of u as small, well, small in absolute value. It's negative, but it's not big. I mean, in absolute value, as small as possible. With smallest possible order of pole at infinity. So we have this nice function now, and so we can consider u omega 1 all the way up to u omega t. These are now meromorphic differentials with only a pole at infinity. Therefore, the sum of residues being 0, these are all differentials of the second kind. And the claim that I want to make is that this set of classes, u omega 1, u omega t, is a basis for H1 de Rham of x. Now, actually, I think I proved this claim, but I didn't do it very carefully in the case where n is prime. And I believe it's true in general, but maybe I'll put this with a grain of salt. This would be a good goal for our group project to actually prove this rigorously or find a counterexample if it's false in general. Okay, so once we have that, we can now just take appropriate linear combination by looking at the period isomorphism. I think the best way to calculate eta g from this collection of data is to, for each of these elements, compute the corresponding modular symbol with values in C, and then find the appropriate linear combination which has the right periods. So we then obtain from this eta g using modular symbols. That's going to be the main ingredient. And then the third step, which is maybe in some one of the more interesting ones, right, which I think was project part C, right? I think part C of our group project is to then find a meromorphic differential alpha on x, regular on y, such that the principal part at infinity of this alpha is equal to the principal part at infinity. Okay, oh my God, here we are. So that the principal part of at infinity of alpha is the principal part at infinity of 2 omega g f eta g. Well, if you look at omega g eta g minus the other thing, I mean, and take the iterated integral, you find that you're led to consider this differential form, which is holomorphic on the universal covering space of x everywhere except at infinity. And so you need to find modulo dq over q. So there might be still a simple Poland difference. And then that's an application of Riemann-Roch, which I didn't get into, but we've been discussing this in the group project. And then finally, once we have that, we need to compute. So now I'm really almost finished. Sorry for. So, what? Oh, here we are. So finally, step 4, the algorithm is to compute. We need also to compute this path, this element gamma e in H1 x naught of n C f isotypic component, which again is a modular symbol algorithm, which apparently has already been implemented by our group. Modular symbol algorithm again. I mean, the key ingredient is again modular symbols here. And then finally, we have our formula. We just have to compute an integral. So our point P of fg then will be, which is this Abel-Jacobi thing, it's just going to be twice the iterated integral over this path gamma e of omega g dot eta g minus the integral of alpha over gamma e. So we've calculated omega g, eta g, alpha, we've calculated omega gamma e, and now we just have to integrate. And that's going to be the final goal, and we hope to implement this on the computer and get a program which will calculate these points by complex analytic means. Okay, so I'll stop here, and sorry for running over time. Yeah, so actually I wanted to add one thing, that I didn't have time to give the proof relating the Abel-Jacobi of the Gross-Kudla-Schoen cycle to the iterated integrals. I don't want to torture the whole room with that thing, which is a bit technical. But those of us who are in the working group, if you're interested in this afternoon, we can find 20 minutes and I can go over carefully the details of that. But it's not needed for the project, strictly speaking. You can take this as a black box if you want, but it certainly is an important theoretical background for that.
Rational points on this.
Exactly. These integrals are they're going to end up giving you rational points on the curve. Yeah.
Yes. But, is there any way to tell? I mean, do you expect to get non-torsion points?
Oh yeah, definitely yes. I mean, they should be non-torsion when, like Heegner points. So when the derivative of the L function is non-zero, and some other L function, like for this point PFG, what controls the non-vanishing of the point is L prime of f at 1, and also L of f tensor sim2 of g at 2.
Sorry.
So there's another L function which enters, which is the, yeah, well, I numbered them. I was careful to number them, but yeah, they're in order. And also I can give you the ones of Victor.
Yes.
Sorry, I don't need them anymore. Yeah. That's a bit complicated. There's a beautiful result of Zhang which says something. Or maybe I should turn this off. So everyone is hearing.
So there were three modules.
Exactly. So in the general formula of Zhang, there's f tensor g tensor. But here we're specialized in the case where two of the forms are equal. And the reason we're doing that, you see, is in general,
Because you choose
with a different product.
You choose this diagonal thing. I mean,
If you look at the motive associated to f, so the general context for Zhang's formula is this. This is an irreducible motive of rank 8, and it doesn't split it in any way. But if you take mf tensor mg, these are the two-dimensional ladder representation attached to G, right? This,
yes, you have a six.
I take H equals G, then you get mf tensor sim2 of G. Direct sum mf some take twist mf of 1 or whatever.
Right.
So this, mf of 1.
So you do expect.
And so you expect that your triple product diagonal cycle is going to tell you something maybe about the arithmetic of f at the central point. And if this, so but somehow this also enters. So like in gross idea, you have the L value of the form and its twist, right? So this is a sort of extra L function that you have to consider. But if that one doesn't vanish, and it follows from Zhang that this point is an infinite. And it's an if and only if. So these points really are. They're kind of natural generalizations of Heegner points.
But you don't see them.
In what sense? Oh, you mean
it's outside of the gross idea.
Yeah. It's really the gross idea for the triple product. I mean, it's a similar phenomenon. So the idea is that we would like to use these points to do for serious arithmetic applications, like Heegner points were used. Now, one drawback of doing that is that these points always tend to be defined over Q.
Yeah, I mean, I thought about just kind of making this diagonal thing in the triple product. You can kind of make it all a certain outlet. The problem is that I mean, you cannot split them. When you
Yeah.
go up the tower, they're kind of continue to be connected.
Yeah, exactly.
So,
Yeah, and you go up, right. So, yeah. So in my last lecture, I kind of indicated that maybe one could use these cycles in more general context, in the context of chaotic information, to get some interesting arithmetic applications towards BSD and Stark-Heegner points. But that, I think, is a possible direction. But before doing that, I want to.
before you get, wait, why? Oh, no. I was thinking, why is L function of that involved in here?
Well, it's just the L function of this modem, if you want it.
I mean, yeah.
So it's the L function at 1 because the take place, and it's the L function of the ladder representation. So in general, what kind of enters is the L function of this triple product.
Right.
But the L function of the triple product when G equals H, the factors as an L function of degree 6 times an L function of degree 2.
I see. So both of them you need to consider.
And you need to consider both of them. So in the situation where the sign of the functional equation for f is -1, then the sign for the other guy is 1. Because the sign of the total thing is -1. So you kind of, this value sort of generically should be, it vanishes to even order at least. So in fact, experimentally, it looks like this is very often non-zero. This one.
Right.
And of course, the derivative is also very often non-zero, so in those cases,
I see.
but it's like with Heegner points that you only ever make a point when you're in a rank 1 situation. You have to be rank 1 analytic.
Right.
But that's life.
Yes. Right. In case, in case you have a, you said you think everything's over Q, and then you have an emergent convective field.